All right, so everyone, Thursday is the exam. We're not taking it here though. All right, so in order for you to get all the time, where are we meeting? Building 800, right? What room? 811, right? Or is it 801? Let me double check. Is it 800 or 811? I know it's building 800. Yeah, 801. So guys, go to 801. Well, we'll just walk over there after class on Thursday. Okay? So room 801. All right. And also the homework. So guys, let's focus. So the homework, make sure you register for active. The grace period has ended. Okay? So if you haven't registered, you can't finish the homework 3. That's due on Thursday, okay, to help you prepare for the exam. So review the homework, study guide, problems we did in class, practice exam, and if you need more practice, do the book problems in the end of each chapter. So chapters 1, 2, and 3, okay? All right, any general questions before we get started? No? All right. So I believe last time we just stopped after the stability of carbon radicals. So we're going to go into why that the stability is in order of tertiary, secondary, primary methyl. Methyls are unstable. Tertiary radicals are stable. Okay. All right. So the reason here. So why are radicals stabilized? Okay. The reason is hyperconjugation. Oops, sorry, misspelled it. All right. Has anyone heard this term before, hyperconjugation? If you took Chem before, you might have heard of this, but let's just say we don't. Okay? So hyperconjugation is like resonance. It's delocalization of a radical, a charge, by the interaction of a sigma bond and a p orbital. Okay? So, delocalization of sigma bond electrons, okay, of an adjacent. So adjacent, another term for that is called vicinal, okay, atom with a partially filled, partially filled / empty, okay, p orbital. Of the other atom. All right, this will be important when we talk about not just carbon radicals, but carbocations, okay? So when we talk about carbocations, not yet, this term here will become important to understand the stability, okay? All right, so let's draw some examples. So let's say I have my carbon atom. I'm going to have my partially empty p orbital, which has the unpaired electron. And now this is just my hydrogen atoms drawn out for clarity here. Okay, so I'm going to draw this bond really long to illustrate the point here. All right, so in Gen Chem 1B, did Dr. Dykes ever teach you the shapes of molecular orbitals? Or that something we never went over? All right, So I'll just show you for illustrative purposes, okay? You don't have to reproduce this. But if you understand this, it might make what I'm about to show you make more sense. All right. So what I have here is a filled. So this is my MO, molecular orbital, for a CH bond, a CH sigma bond, okay? It looks like this. All right, my hydrogen will be here. Let me put 2 dots in red to illustrate that that's a bond, okay? And here's my H, all right. So I have to shade this part of the orbital. So the things about molecular orbitals, they can't form a bond unless they have the right symmetry. And symmetry has to do with like advanced mathematics that we won't talk about, okay? But basically orbitals have signs. They're shaded or non-shaded. That's the sign of the wave function. And in order for them to interact or bond, they have to be the same color, okay? So that's why I shaded it the same color here. And what we get is a bonding interaction here, or an interaction with these orbitals, okay? Like that. So what the CH bond is doing, it's donating some of its electron density to the p orbital through a sigma bond, okay? Not through a pi bond where we moved it. Here, you're not actually moving any atoms, but you're delocalizing these electrons in there through the p orbital, so you make it more happy, more stable, okay? And then the rest of the atoms here, we have a hydrogen and then a hydrogen sticking in the back, okay? So these interactions occur between any CH bond and CC bond adjacent to the p orbital. All right, so this would be an example of a ethyl radical. Like that. Okay. Are there any questions about that? It may sound vague right now, but that's okay. This is a very abstract concept. Okay, but that's how we rationalize the stability of radicals. These carbon-based, these CC bonds, they are donating groups. Remember, electron donating groups. That's why. So that's the application of this. All right, so let's do another radical here where we show now a secondary radical. Okay, so let's draw the carbon atom again. I'll try my best to draw this to the best of my ability here. So I'm just going to shade it like this so we can actually see the electrons still. So here I'm going to draw a radical that's stabilized by 2 CH groups here. Oh, sorry, this is dashed. I didn't mean to put dotted lines. Okay, so there's one interaction here. Okay, but then there's also going to be an error. So I'm going to try my best to do this. So sticking in the back is that H. And sticking out in the front here is my CH3. So I'm going to put the CH2 of the hydrogens not shown. And then I'm going to show one of these orbitals here for the CH bond. Like that. And what we get there... Okay, sorry, we have to shade this one too. All right, and then this is actually, let me just draw this in a different color so you can see that it's overlapping and interacting with the central p orbital of the radical, okay? So here is my p orbital with single electron, okay? So this is the 1-methyl ethyl radical. All right, and this is also called the isopropyl radical. So you could call this the isopropyl group too. All right. Great questions on what you're drawing right there. All right. So the key thing here is the structure of this this radical here explains its stability. Okay. So you form the most stable radical. It's usually the one that further reacts. Okay. The easier it is to form, the faster it will react. Okay. All right. So let's do one more example for radicals. Stability, that is. Okay. All right. So let's do the tert-butyl radical now. Are there any questions though? So far? No? All right. So let's just zoom down here. Scroll down. All right. So now we're going to do the tert-butyl radical. So let's draw a new p orbital like we did before. All right. So here is the orbitals I just drew here. All right, so this one is interacting here. And then there's also two hydrogen atoms bonded here. Okay, now this one we have to draw a little bit carefully here to be able to see all these atoms. Okay, so we're going to have CH2, and I like to draw it like this. So this one is interacting with the p orbital. And then we have another one interacting here. So maybe I'll draw this one in a different color so we can see the lines better. All right. All right, so this one's actually interacting as well. So that's why we draw them in the red line. So in this case, we have 3 CH groups, CH bonds, stabilizing this radical. And if you were to rotate some of those other H bonds, you can actually see that the other CH bonds can donate electron density 2 into the p orbital with the radical, and that would stabilize it. Okay? So we'll see how this applies when we determine reactions, the products, okay? So tert-butyl here, CH3, and then CH3 over here. Boom, okay? So this will be the 1,1 dimethyl ethyl radical. So this is also called tert-butyl. All right, are any questions about that? So this is pure abstract, so what I want to do now is actually show you a little movie where it animates this, okay? I didn't get a visual aid there, will be much better, okay? But are there any questions before I do that? Any questions? Clarifications? No? All right, so finish writing that down, and I'll show this little clip here. All right. All right, and guys, remember on Thursday, there's no lab, okay? So just show up, take the exam. You got 3 hours, but I made the exam to be completed in 50 minutes, okay? But you get that extra time if you need it, okay? I'm not going to make it super hard, okay? That's not the goal. Sure. Yes? So it starts at 12? No. So we'll start at 3 p.m., and then you'll have 3 hours till 6 to complete it. So we'll take the exam in lab. But still show up, because I'm going to still have to do a little lecture on exam day, okay? Yes?
That practice exam you posted on Canvas, is it like similar?
Similar format, similar length.
Similar length, okay. But it's not like, I felt like number 2 we didn't practice.
Don't worry. Some of that stuff, remember, that's why I come to class, because I'll mention some of that stuff you shouldn't worry about. Okay. Yeah. Cool. Thank you. You have any other questions? Just a few aspects of it, like the reaction part. Don't worry about how All right, so let's do a little clip here. All right, let's see here. Where's hyperconjugation? Is it on here? I thought it was. Oh, here it goes. Here you see. All right. All right, so let's look at hyperconjugation. So we saw this before, right? Tertiary is the best. Methyl's the worst. All right. Okay. Okay, let's see this. All right, so we can see how their methyl groups are kind of aligned there. Secondary, primary, and then methyl on the very top, okay? All right. So what this is saying is that the most unstable radical is less methyl groups around it, less substituted. Okay. And we can see here that that electron in the p orbital is somewhere in this p orbital, right? And we can see here that if we have hyperconjugation, okay, there's going to be some orbital overlap. See, the electrons now are being shared between the CH bond and the p orbital. So the more interaction you have there, you'll make it more stable. That's what we're trying to show here. Okay? All right. So that's what I like to show. It's a really good kind of visual aid there to see how what's actually happening between these electrons. But notice here that no bonds are breaking or forming like we saw with resonance structures, which is a similar effect to hyperconjugation, but with pi bonds and lone pairs. Electrons that can actually move between the molecule. Okay, are there any questions about that? You can actually watch these. I'm pretty sure I linked them through Canvas on YouTube too. So if you need a visual aid to help you understand these things, I would totally recommend it. All right. All right. So now we're ready to talk about free radical halogenation, the only useful reaction for alkanes, okay? Other than combustion, okay? So understand combustion. What are the two products of any combustion reaction?
Carbon dioxide and water.
Yeah, that's all you need to be able to write, okay? If you see combustion in there, oxygen and heat, bam, you should think combustion, all right? But now this one's a little bit different. We're not going to use oxygen gas. We're going to use a halogen as a gas, or bromine as a liquid. All right, so free radical halogenation of methane. Okay. So we like to introduce this reaction first because it gets you in the habit of trying to predict the products of a reaction, okay? So let's try methane. Methane's a gas. So you just put methane and you put in with chlorine with no added temperature or other energy source. You get no reaction. All right. Abbreviation you can write here is NR. That tells me you don't think a reaction occurs. And sometimes that will happen. Sometimes you get an NR on an exam. But you won't always get all NRs, okay? That will sound fishy, okay? So, in order to, the reason why this reaction doesn't really go is because you need to initiate it first. Because we can see that this reaction is favorable if we calculate the bond energies, okay? So let's do delta H here. All right, so this is going to be the bond energy for my reaction. All right, so let's just write the reaction here. So we're breaking CH bonds. That's why I wrote CH3H in the gas phase. All right, so this bond energy is 105. And then we have to break a chlorine bond, so ClCl, that's 58 kcals per mole. Now, this reaction will proceed to the right to form methyl chloride, CH3. So what you're doing here is substituting a hydrogen atom for a chlorine atom. So that has some uses to make it more functionalized. Okay? And then you have HCl. Oh, sorry. Don't write that yet. Draw out the bond. So you have, hopefully you have a pencil eraser. Okay? And in the gas phase, this is 103 kcals per mole. All right. You guys remember how to calculate delta H for a reaction if you're given these values? You might have to do, don't worry, you don't have to do this on the exam. But this is something to look for in the future, okay? Do you guys remember? How do I calculate delta H of reaction if I'm given bond energies? You're close. Not exactly in this case, not with bond energies. You'll be right if you were using actual enthalpy values. All right. So in this one, it's the bonds that are broken minus bonds formed. So let's look at what bonds are being broken. So in the reactant side, what kind of bonds are being broken? Methane gas, thank you, Captain. Methane gas, and what else? Chlorine. So 105 plus 58 minus, and the bond's being formed here, CCl, right? And what other one? HCl, thank you. Okay. So if we add those two together, we will get negative 25 kcals per mole. All right, so clearly this reaction is exothermic, so it should be favored to proceed, right? But there's a problem here that even though it's favored in terms of thermodynamics, it's actually not kinetically favored, so it has a activation barrier. So we need to kickstart this reaction actually, okay? So this reaction actually proceeds if we give it some energy, okay? So here is the reaction here. CH4 gas plus CO2 gas, chlorine gas. All right. So you either need to stimulate this reaction using radiation, light, or heat it. So delta here stands for heat. And the temperature you need to reach is 300 degrees Celsius. So a pretty high temperature. You probably won't do this on the bench. You need like an autoclave or something, okay? Where you achieve high temperatures. All right, so this will achieve the reaction for methyl chloride, which is a gas, plus HCl in a gas state. So the driving force for this reaction, you're taking nonpolar bonds, CH and Cl-Cl bonds, and you're replacing them with stronger polar bonds, CCl and HCl. So that's the driving force. Polar bonds are stronger, so if you can form stronger bonds, that's going to be exothermic. But as we see here, we need to kickstart it with some energy, and that's usually the case for most reactions. Like, burning gasoline, you put gasoline near oxygen, it won't do anything. You need a spark to get it going, right? Okay, how's that so far? Any questions? Because now I'm going to jump into the mechanism, okay? Which is a little bit involved. All right, so this mechanism will be a brief introduction to most of the mechanisms we'll see in this class and in 18B. All right, so there's 4 steps in this mechanism. The first step is to initiate. That's called initiation. All right, so number 1, initiation. That's where the heat comes in and the light. All right, so Cl, this will break homolytically. So each chlorine gets 1 electron each. All right, and you can achieve this with either temperature or light, okay? So either one. So maybe put like a slash mark here, sorry. I didn't mean comma. All right, so you get 2 chlorine atoms or radicals. So I don't show the other lone pairs just to keep it concise here. But this chlorine actually has 7 electrons, but the 1 electron is the radical. That's reactive, okay? All right, so we call this a radical reaction, and we often call it a radical chain reaction, because once you get it started, it'll just keep going over and over and over and over again until all the radicals are consumed. Okay, that's what that means. So this is called the first propagation step or chain lengthening step. So we call this step 1. I'm going to abbreviate this as PS1 from here on out. All right, so what happens here is your methane molecule will now be able to donate a hydrogen to a chlorine radical. So your chlorine radical here is going to come and approach and use a single arrow. This hydrogen is going to be removed, and this radical returns to carbon. So this is called hydrogen atom abstraction. You're removing hydrogen from the compound, okay? All right, so the result of this is the methane molecule becomes methyl radical, so that's CH3 dot. And then your first byproduct is formed, HCl. See the chlorine radical got an H and became HCl. So this is your first byproduct. All right. And the result of this step is slightly endodermic. So your delta H here is actually positive, but not by a lot. Plus 2 kcals per mole. Like that. Okay. All right, any questions how we drew those arrows? So radical reactions, always homolytic cleavage. So you're only moving 1 electron. So we use the fish hook arrows. Half-headed arrow. Don't ever show double-headed arrow. That'll be considered incorrect, okay? But any questions about the notation there?
I have a question.
Yeah.
Why is there not a 2 in front of the chloride that has a radical?
Oh, okay, so only 1 gets used. Yeah, so that's just a source of radical. So in these reactions, sometimes they won't be balanced. So don't be alarmed by that. That's totally okay. Okay. What we could have said is that 2 of these methane molecules react with 2 chlorine radicals to produce 2 methyl radicals. But I didn't write that just to be for clarity's sake. All right. All right. So the third step is propagation. Step 2. All right, PS2. Not to be confused with the console. Okay, so you have now what happens here is this is going to regenerate the chlorine radical and repeat the whole cycle over again. And this is what we call a radical chain mechanism. Okay, it just goes over and over and over. All right. So chlorine will react with the previously formed methyl radical. Sorry, I might have to draw some weird arrows here, okay? So boom, boom, and then this returns to chlorine, and then this will now produce your product, methyl chloride or chloromethane, CH3Cl, plus regenerates your chlorine radical. Oh, look at here. We got the radical back. That can re-enter step 2 and do the whole sequence again. Okay? All right? So you might be asking, wait, always going in the loop, won't it never end? Well, when you form radicals this way, there's always a chance that there's an event where these two radicals will meet and terminate. So the fourth step is called termination, all right? But first, let's write the energy here. So notice this energy is very exothermic. Delta H of this step is negative 27 kcals per mole. So the only barrier is to get to the coring radical and then pass the first propagation step. If you get past those, the second step, the third step, is usually very exothermic, that this reaction will just go to completion, or, favored for the products because of the second propagation step. Okay? All right, so termination step, there's 4 kinds, okay? So just be aware of the 4 kinds here. Termination steps. So the only way this chain mechanism can end is if 2 radicals come together. So this happens if 2 coring radicals react and reform coring gas. So you can get this as a termination event if the coring radical and the methyl radical come together. All right. So this just further complicates the process because of these termination events. Okay, so that's why radical halogenation is sometimes very hard to control. Okay, and then this one, a product you probably did not expect, 2 methyl radicals joining together here. And this event is very rare, so it rarely happens. You can get a side product, you can get ethane gas. Okay? So if ethane gas was your target here, you wouldn't actually use this kind of reaction because the yield would be very low. So there's ways to generate 2 radicals coming together, but radical halogenation is not the answer. Okay, that's not the way you do it. There's more sophisticated ways. All right, are any questions about these arrows? So the best way to understand this, don't worry about this for the mechanism, don't worry about it for the exam on Thursday, okay? A little too much. What I want you to think about is that I can substitute hydrogen for chlorine by doing radical halogenation. So you should just think of the products there. The organic products, you don't have to write the inorganic product. We don't care about that. Okay, so let's draw this schematically here and show what this looks like on a graph so we can kind of see how this reaction transforms over time. Okay, but are there any questions? Okay. So let's draw an energy diagram. So with reactions, it's often good to draw energy diagrams to kind of see how it changes respect to energy. Okay, so all right. So here we have energy on our y-axis. Okay. So in the middle or slightly above here, I'm going to draw this line. So this would be my first propagation step. Cl radical, okay? And there's also plus coring gas that we had before. So those are my reactants, okay? All right. So now let's draw a little loop here to my first bump. And then there's going to be a product right there. And then we have a state up there on top of the peak like we saw with conformations. And then we have this area right here, the products, which is methyl chloride plus HCl plus regeneration of the chlorine atom, the chlorine by itself, okay? All right, so let's just draw a few dotted lines. Boom, 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 boom. Like that. Okay, so this is our activation barrier. Our first one, E of A, okay, is 4 kcal per mole. Like that, okay? So, to get from our reactants to the first so this top part is called the transition state. That's our transitory period between reactants and products. All right, so we denote transition states with this special symbol. We call it double dagger, okay? So this is called my transition state. All right, so my transition state, it's actually not a molecule per se. It's a phase that exists, theoretically speaking, between reactants and products as bonds are breaking and forming, okay? So H3C here. In this first step, what's happening is its hydrogen atoms is breaking, so I denote that with a dotted line, and then the chlorine atom is forming a bond to it like that. And we usually represent this in brackets, so I can rewrite this as H3C dot 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 H dot 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 Cl. And to denote this as a transition state, I could put double dagger here, and then I put a little dot right next to it to indicate that this has radical character. So a radical is forming, okay? All right. After that, we get our methyl radical, because that's what's forming, right? The methyl radical is forming, and I'm producing, I still have Cl2 here because it's one of my, I didn't use both, I have Cl2 there because of the reactants, okay? Plus HCl, like that, okay. So now let's calculate the change in energy from my reactants to my first. So that little dip, that state is called our intermediates. It gets made, then immediately gets consumed in the next step. That's what an intermediate is, okay? So if we draw another dotted line, let me just notate it in red. So I'm drawing this red line to this bottom part. All right, so this here is my delta H of the first reaction or the first process, and that is 2 kcals per mole. Okay, sorry about that. Let me just write here, this is in kcals per mole. Okay, so remember that step, you increase in energy, but that's okay as long as the next step kind of compensates that by having a low activation energy and a larger release of energy, okay? So now let's go, so now let's draw a dotted line here. So what was our, does anyone remember, what was our delta H for the whole reaction? What value was that? You guys remember on the previous page? Thank you. Yes. Negative 25 kcals per mole. So our reaction is still okay. It can go further as long as we don't need additional input of energy and that the input, the energy released is negative numbers, negative 25. So we just need the next step to be negative to reach this value, okay? So let's go here. Now we have this state, okay? So the distance between here and our starting point there, okay. So I can't fit any there. So here, the activation energy is less than 1 kcal. And that's good because now we have enough energy to get over that activation barrier and proceed to products, okay? So this reaction here is actually much faster. So as long as you have a faster second step, you can proceed kinetically, or in terms of reaction rates, proceed well to the final product. All right. So now here, let's draw the second transition state here. So I can't really fit it up there. So here is my second transition state. All right. So another double dagger event. H3C is now going to interact with a molecule of chlorine, and chlorine's bond is going to break. Okay, so this also has radical character because we are interacting with a radical, and the chlorine atom or radical is being produced again. Okay. Boom, okay, like that. And now we can just denote this as a radical, and this is a transition state, so that's usually the symbols we use. All right. All right. Are there any questions on that one? On what we just drew right there? I'm just showing you the transformation of those steps, okay? All right. So now let's finish this graph off, and we're going to write the energy change between this step and this step. So this is the delta H number 2, all right? And this is equal to negative 27 kcals per mole. All right? So if we add the delta H's of both steps, they equal to delta H of reaction, and that's how you would draw it on like a graph, all right? But now this x-axis is now reaction coordinate, and what happens in the reaction coordinate is you're going to, at the left side, you basically have the HC bond going to, is breaking, and you're forming an HCl bond. And then at this midway point here, okay, this midway point, what's happening here is you're reacting a CCl molecule, and that CLCl bond is turning into a CCl bond as we get to the end here, right here. Okay, so that's what's happening here. The bonds are breaking, new bonds are forming. So you go from an HC bond in methane to a new CCl bond in the products at the very end, right there. Okay, so that's how we represent transformation of reactions on a more visual cue here. All right, are any questions on that? No? All right, so before talking about more of that, let's take a little break, okay? So 10-minute break. I need to get some water, and I forgot my water, so I'm gonna go get it. I'll be right back.
Oh,
right. All right, guys, let's continue with calculating. All right, let's settle down. All right, so we saw the mechanism. Now let's calculate. Let's see how the halogens relate to what X is, okay? So, calculating radical halogenation of methane, okay? All right, so CH4 plus some halogen gives us CH3X plus HX. All right, so this is not feasible for all halogens, and that's because just some of these halogens are not reactive. Okay, so let's draw a box. So we're going to have our halogen on the left column. And then our delta H value. So this is our bond dissociation energy, okay? kcal per mole. All right. So this would be bond. All right, let me see if I could write it. Dissociation. Oh, such a long word. Okay, bond dissociation. Basically, you break the bond and give the electrons to each of the atoms of the bond. Okay, so F2, fluorine, actually not that bad. So fluorine is actually so reactive that we'll see that fluorine is too reactive. Okay, and a big part of it is the small bond energy and the reactivity of the fluorine atom. Okay, so chlorine is a useful one, as we'll see here, 58 kcals. Bromine, 46. So it's interesting, chlorine and fluorine, why they're kind of, you would think fluorine would be the strongest bond because of electronegativity, but that's actually the reason why it's so weak. Fluorine is so electronegative that the repulsive forces, fluorine is also small. The repulsive forces are so close together, it makes that bond essentially weaker than a chlorine-chlorine bond. Okay, so that's why it's 37. All right, let me just truncate this a little bit. Okay, so those are our energies for the halogens. So now let's see if this reaction takes place with all of them. Okay, so let's draw another table here. All right, so bear with me. Enthalpies of the propagation steps in halogenation of methane all right, and this is in kcals per mole. All right, so let's write here our reaction. Okay, so first propagation step. All right, so the X atom will have 7 valence electrons. All right, so it's reacting with CH4 to give methyl radical and HX. All right. So the energies will depend on what halogen you are talking about, okay? And like we saw with chlorine, the first step is usually positive, okay? And that's usually what we see here. Oh, but for chlorine, it's the opposite. Chlorine is so reactive, it's negative 30 kcals. Chlorine, we saw, was plus 2. Bromine is plus 18. And then iodine is the complete opposite of fluorine, very endodermic. So right out the gate, not very promising signs that this will work with iodine, okay? All right, now we have propagation step 2. Okay. Actually, guys, you don't have to put this here. Sorry, I don't know why I put that. All right, the methyl group, the radical here, will react with another molecule of your halogen to give CH3X plus regeneration of your X radical. And you see your X radical here can go on and be reintroduced into propagation step number 1, okay? All right, for fluorine, this step is very exodermic, negative 73. So fluorine is the craziest. It's the most reactive, followed by chlorine, bromine, and then iodine. All right, and then if we sum these steps up, we can get the delta H for each of these halogens. And we'll see if they all work or not. So this reaction will only work if they're overall exodermic. If it's endodermic, you need to keep supplying energy to get this process to go, so it's unfavorable. All right, so CH4 plus X2, and if you see this, the radicals can cancel out. And then X radical will cancel out, and then you're just left with the species that remain, like how we balance ionic equations plus HX. Okay, so for fluorine, this is great. Negative 103, a bit too reactive. So fluorine doesn't have much uses. It's too reactive. All right, chlorine, negative 25. Bromine, barely exodermic. Oh, but look, iodine, positive 13. So unfortunately, we cannot get iodine on carbon this way. It won't work. All right? You have to get iodine on carbon a different way. So this method won't work. Radical halogenation, iodine, no go. Okay? So let's now summarize the relative stabilities of, not stabilities, reactivities of the halogens at removing hydrogen atom from methane, okay? So here we could write relative reactivities of X in hydrogen. So this is abstraction. Removing hydrogen, that's called hydrogen abstraction. I know it sounds kind of weird, but okay. So fluorine atom or radical, much greater than chlorine. This is much greater than bromine, greater than iodine. And you can think of this in two ways. Fluorine is electronegative, so there's no way it wants to stay that way. It wants another electron, okay? And as you go down the column, the size of the atom gets greater. So that electron is not going to be that reactive because it's kind of stabilized by the large size of the atom. Like we said about radical stabilities, the size will kind of help accommodate the radical more easily. Okay, so right here is least reactive. And then on the left, most reactive. All right, are any questions on the relative reactivities of the halogens here based on the radical that forms? All right, so we're going to put this into practice now. Looking at other alkanes, All right, so we're going to start with ethane, and we're going to start with chlorination. All right, so let's start thinking about chlorination. We'll skip fluorination and go back to it because fluorination is not that useful. Okay, so, all right. So, for our purposes, we will focus on just monochlorination or monohalogenation, where only one halogen replaces a hydrogen. Now, that's not always the case. You can get double replacement, where more than one halogen replaces hydrogen, but that gets confusing, so we're not going to talk too much about that, okay? But that's possible. The only synthetic use of this reaction is when you get one X on the carbon atom, okay? So, monochlorination of ethane. All right. So let's start with this. Ethane here. So we're going to talk about higher alkanes. So here we're going to talk about relative reactivity and selectivity. All right. Higher ordered alkanes. So higher alkanes. Let me just put that as a summary here. Higher alkanes. That's what we're focusing on. Okay. So CH3 plus chlorine here. All right, this reaction will go either with light, irradiated, or 300 degrees Celsius. All right. So, well, both those methyl groups are equivalent, right? They're symmetrical. So it doesn't matter where you put the chlorine on there. You're going to get only one product, CH3, CH2, Cl, plus HCl. So this is something you might have to do on Thursday, okay? You're given a reaction, produce the major product, all right? Would be the major product. There's no matter how you draw it, it's going to look like that if you just get one of them on, okay?
Not the HCl, the CH.
Yeah, just the organic. We just care about the organic product. HCl would just bubble out of solution, so you're fine, yeah.
Okay.
Good. Don't worry about the delta H's. That's not required for this test, okay? So negative 28 kcals per mole. So see here, slightly more exothermic. And that might have just to do the fact it's a higher ordered alkane, okay? All right, so let's practice the mechanisms. So we practiced this, I think, a few times with different structures. I think the procedure becomes more routine, okay? So let's start with the mechanism. All right, so first is initiation. All right, what happens with initiation? Our chlorine molecule does what? Splits. Thank you. Splits evenly, okay? So we're going to get 2 chlorine atoms. And the way you do this is you use UV light or, blue light, or you can heat it to 300 degrees. Nowadays, to be more green, we try to use microwave irradiation or a radiation source, like a blue lamp, a colored lamp, LEDs, trying to be more green, okay? Heating it is not efficient, energy efficient, okay? So that's the first step, right, initiation. Then we have propagation step number 1. The hydrogen here from ethane is going to be abstracted. So our chlorine atom here is going to come by and take this hydrogen, and then this is going to return to the carbon atom of ethane. So you're going to end up with a ethyl radical. All right. And then your byproduct here is HCl. So for mechanism questions, you have to balance all the atoms, and it looks something like this. But we're not going to worry about that yet, okay? Because we just saw our first mechanism today. All right, delta H in this case is -2 kcals. You don't have to remember these numbers either, okay? They're more important for like when we calculate delta H, but we probably won't do that just yet, okay? All right, the second propagation step, my new carbon radical is going to react with what? Yeah, the other chlorine, okay? So it's not actually the chlorine radical, but it's another molecule of chlorine, okay? So, well, you don't have to, it's all right. Let's draw it this way. CH2 radical plus chlorine molecule, or the chlorine, molecular chlorine. All right, like that. And then we get, sorry, I might have to draw a weird arrow here, not balanced. CH3, CH2, Cl, okay? Plus chlorine atom right there. And now this step is what drives the reaction to the products, -26 kcals per mole. All right, and so that's the mechanism there. And that's pretty much all the steps you would have to show if I asked you to show a mechanism, but I won't, okay? So ignore that question on the practice exam, all right? Not yet. Okay, are there any questions about ethane? Here? So this is what we call electron pushing mechanism or arrow pushing. That's the term in organic chemistry. And yeah, it's been here forever. There's not a better model to kind of, convey this information. Of course, there's background why this happens, but that would have to, we would have to talk about orbitals, molecular orbitals, and that's a little too advanced for this stage, okay? So this is our best guess here. Yeah, Catherine.
So then would we do a termination step?
No, don't do a termination step unless I asked you. Yeah. So the reason for termination, so I don't want you guys to write it right now, and that's because they're very rare. So they're statistical. It's a statistical probability, and it's very rare in a chain mechanism. So don't worry about that, okay? What's important is starting the reaction, initiation, and then propagation, extending the chain reaction, okay? All right, so now that's ethane, but ethane is a little too simple. We need to go a little bit higher. So let's go to propane. So propane, okay? So let's look at propane. All right. CH3, CH2, CH3, okay? All right, so we're going to do monohalogenation, okay? All right. All right. So this one's a little more complicated. Because how many products could you draw with just one chlorine in it? Can I just draw one? What do you guys think? OMG. I'm not too close. All right. I do that on my phone because at night, my phone is too close to my face before I go to bed. So, yeah, I even set a timer to try to limit my phone time. I forgot to take it off for the iPad. But anyway, are there any, how many products? Sorry, train of thought just got lost. How many different products can we draw? 3. Why would we say 3? So look at the two methyl groups. If I just drew one chlorine at either end, are they the same or are they different?
They're the same.
They're the same. So 3 is a good guess, but it's actually 2. All right. I could put one where the methyl group is, or I could put the CO where else? Yeah, okay, I think I know where you're going with that. Yeah, sure. CH3. So we just put this at the end, right, with the methyl group. So let's say this is product A. But we could also put it where? CH3, CH, Cl in the center, right? CH3. So one is where I have a primary chloropropyl group, chloropropane. And the second one is where it's attached to the secondary carbon, 2-chloro propane. All right? So now we got to ask ourselves, what's the theoretical? So this will be theoretical yield. And what's the observed or actual yield? All right. So the theoretical yield is based on statistics. So in product A, how many hydrogens do I have there that if I reacted it once, I would get product A? So how many potential hydrogens can give the same product? 6. Good. So we have a total of 6 potential hydrogen atoms turning into product A. And how many hydrogens are in the molecule? 8. So if we divide that and times by 100, our yield here for A should be 75%. So that's pretty high. Now how about B? How many hydrogens are there that can react to give B? 2. Very good. So 2 out of the 8 hydrogens can give us that value. And this would equal, sorry, let me just times it by 100 first. Oh, that's why we don't put equal sign. 25%. All right, in actuality though, that's not what we get. And you can't guess this. 43% is what we get of A. And then 57% is what we actually get for B. So it is not statistical. There's some inherent reactivity at work here. Okay? So 43% we only get of A, as opposed to 75% of the theoretical, and then only 57% of B, so a lot higher than our theoretical. Yes?
What did you get 6 hydrogens?
Oh, 6 hydrogens. Okay, so look here. I used one of these hydrogens to get A, right? But I could have used these hydrogens and these hydrogens. Any one of those hydrogens can be converted to chlorine to give me product A, right? So that's where the 6 hydrogens come from. So we do 6 divided by total amount of hydrogens times 100. That's 75%. Okay? And then likewise for B, if we look at the central hydrogens, there's only 2 here. So that's why it's 2 over 8. Okay? All right. So the percentages here are quite similar. All right? So it's not completely statistical. For chlorination, it will depend on both the relative reactivity and the number of hydrogens present, okay? So we had more like, it's almost a 50-50 mix, okay? But there's some situations where the less selective one or the primary one could actually win out, okay? All right, so that was propane. Now let's talk about these rates, okay? So let's summarize this. So we have coronation. Of alkanes. Relative reactivity of the hydrogen, okay? So each hydrogen is different. All right, so what we compared in the previous example is the relative rate or relative reactivity of a secondary hydrogen compared to the relative reactivity of a primary hydrogen, okay? So the way we calculate this, all right, we're going to have a complicated fraction. So 57%, so that's the yield of my secondary product. So we need to normalize these yields, okay? Because 57 was for 2 hydrogens, 43 was for 6. So you can't directly compare them. You have to normalize them to 1, okay? So 57 divided by 2 here, that's the number of secondary hydrogens, all right? So what this means is these hydrogen atoms were on a secondary carbon atom, all right? Be able to identify those different types, okay? All right, let's put this in a bracket because we have another fraction we have to compare. So put this all over 43, and that's the yield of the primary product, so 1-chloropropane. And then we divide that by the number of hydrogens here, 6. And that's the number of primary hydrogen atoms. All right, so put that in brackets. All right, so if you simplify this fraction, the ratio here is close to 4 to 1. All right, what does that mean? My relative rates are 4 to 1. Which one's faster? The top one. So the reactivity of the secondary hydrogen is 4 times as fast as the primary one. So that's why we see a greater yield, even though there's less hydrogens available, 2 versus 6 to react, okay? So here, coronation, we'll see coronation is one of them that's a little more selective than, say, fluorine, okay? All right, are any questions on these numbers? What's the most important here is the relative rates. So in this case, you should just memorize them, all right? So a primary hydrogen is very slow compared to a secondary hydrogen in coronation, okay? All right. So let's just show how these products came about. We're going to do the mechanism again. So, yes, what's up? Oh, yeah, sure. So look at B, right? B is where I put the chlorine on the second hydrogen, right? So there's 2 hydrogens there that can possibly react. And this 57 is from experiment, okay? So it's not some number you can just guess. It's from experiment, all right? So that's B. And A here, A is on the methyl groups. So there's 6 possible hydrogens to react. And that's where 43 came from, 43%. Okay? All right. And that's where those numbers come from. So the 2 comes from those 2 hydrogens, and then the 6 hydrogens come from those methyl groups at the end of propane there. So that's 4 to 1. All right. Are there any other questions, though, on that? No? All right. So let's go over the mechanism again here, just for practice. CH3, CH2, So propane is reacting with chlorine, right? And there's two possible ways they can react. Right here, one of these hydrogens, or one of these hydrogens right there. All right. So all right, so let's go, let's do the primary hydrogens first. So the primary carbon atoms will react first, okay? So we have chlorine atom here reacting with one of these hydrogens. So it's one of these hydrogens on the end, and this returns to the carbon, like so. All right, HCl is a byproduct that forms initially. And then we have our radical, our propyl radical here. CH3, CH2, and then C radical, H and H. All right? Okay, so this is going to encounter another molecule of chlorine or atomic or elemental chlorine here, how it exists in nature. And bam, it will combine there and with that chlorine. And then it will give us the first product, CH2, CH2, Cl. Okay. And then the radical here. Boop, 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 boop. All right. All right. So can we name that first product? What's the name of that first product? Any ideas? A little practice here. What is it? So I like it chloropropane, but I think the number we could do the number should be lower. Yeah. There you go. 1 chloropropane. Very good. All right. So let's do the second route here. So that's the first route. Product A. This is product A. Now let's go to product B. So I'm just going to write them all out in lines here. All right. Just because we have to decide which carbon and hydrogen we're going to react with. Okay? All right. So we're going to have a chlorine radical again. So now this hydrogen, the central one, that is the one that's going to react. Like that. Okay? So again, we get HCl. But then we also get H, C, H. All right. So this radical is going to remain and react with another molecule of chlorine. So we're going to do plus Cl, Cl. Now this one will now react with this radical. So sorry, let me just draw it around there. Okay. And what we get here is CH3, CH, Cl, CH3. Okay. What's the name of this one? You got it. There you go. All right, so that's how both products form. Are there any questions? So think about the mechanism. Not very different. You're just forming a different radical, and you're just removing a different hydrogen atom in both cases. Okay, and then the chlorine attaches to that hydrogen atom or the carbon from where that hydrogen atom was removed. Okay. All right. So we talked about primary and secondary radicals. Now we're just missing one more. What radical is that? Tertiary. And we're going to see if it's as reactive as the secondary, okay? And we'll find out. All right, so let's draw a line here. Mono coronation of tert butane. All right. So very similar reaction. We're just taking away a different hydrogen, okay? So H3C, C, CH3. All right, so we're taking away that hydrogen. And it's still with chlorine, okay? Chlorine's a good example because of these relative rates. So you can use light or 300 degrees Celsius, and you get either of two products, H3C or H3C CH CH3 CH2Cl. All right, so first off, right off the bat, let's just name these two products. What's the one on the left? All right. All right, I heard two answers. Good. So 2-chloro, 2, yes, propane. All right, and then what's the one on the right? It's very similar, but not, we'll probably have different numbers. So maybe do 1, 2, and 3. So we get 1-chloro. Thank you. All right. So guys, if you can name them differently, they're two different products. Okay? All right. So now let's talk about what we actually think will happen and what is the actual yield. So now we have theoretical yield. So this is statistical and expected yield. Okay, so there's only one hydrogen for the first product, and there's 10 in total. So we think this should only form 10%. And then this one, since there's 9 of these hydrogens, 90%. All right. The expected ratio, though, is quite different. Sorry, I meant to put ratio here, not ration. Okay, it's actually 36%, and here it's 64%. So here, it looks like the statistical ratio, so the more hydrogens that were present, won out, right? It looks like that was the major product. But it's not in the numbers we expect. So there should be a relative rate that we can calculate too. All right, so let's write that right here. Relative reactivity. If you want, you can just write relative react of a tertiary hydrogen over relative reactivity of a primary hydrogen. So if we know this rate, we can order the rates of primary, secondary, and tertiary hydrogens. Okay? So here, I'm not going to list the labels again as in the previous page. So 36% for every 1 hydrogen over 64% for every 9 hydrogens. Okay? So it doesn't matter what compounds you use, as long as the numbers are consistent, the rate should be the same. So this will equal approximately a ratio of 5 to 1. Okay? So it looks like the rate of a tertiary hydrogen for chlorine is not that much different than secondary. Okay? So let's look at the relative, let's order them now. Relative reactivity of a hydrogen in monochlorination. All right. So the order is tertiary to secondary to primary. So the relative rates are 5 to 4 to 1. All right. So what I wanted to mention here is, I want to mention something, okay? Let's see here, okay. All right. So, since the rates for tertiary and secondary are so close, let's make this a little note here, okay? So, for chlorination, okay, so that's a comma. For chlorination, both reactivity, so the rate, so both reactivity and number of H's. Sorry, let's start right. Number of each type. All right, my bad. Each type of H must be considered. Okay? So, to calculate the reactivity here, you're going to do reactivity of a H in monochlorination okay, you're going to take the number of H, okay, and you're going to times by the relative rate or relative reactivity. And we'll go more into that next time, okay? So, yeah, let's end it there, okay? We'll talk about fluorine, bromine next time, just before the exam. And if there's any general questions, I'll stick around for a bit, okay? All right, good work.